Questions on the homework?
There's like a rating.
I had a homework problem.
Huh?
I had a homework problem. Yeah. Y equals X.
What number?
I didn't write the number.
It's,
I just give you the question. Y equals X, sine 1 over X.
like that?
Yeah. Find the derivative.
That's number 32.
32. How do we do it? Product rule, right? We have two functions multiplying. There's an x and then there's a sine of this thing, right? But it's not just the product rule. To differentiate this part, what do you need? Chain rule. Probably to make your life a little easier, you can think of it this way. X to the minus 1, so you use the power rule. It makes that easier, right? So y prime equals, differentiate this, leave that one, right? So it's just sine plus, now you leave this one and differentiate this one. How do I differentiate that? Cosine x to the minus 1. And then you multiply by the derivative of the inside function, which is minus x to the minus 2. So this is just sine x to the minus 1. Here, remember, x to the minus 2 is just 1 over x squared. This guy's going to cancel with one of those. And so you'll have plus minus cosine x to the minus 1 over x. Questions on that? So overall, you use the product rule because we have a product. However, the chain rule to differentiate this guy. Okay, so sort of the idea is when you're applying derivative rules, you sort of look from the outside in. Overall, there's this huge product, but then within the product, this factor, you need the chain rule. Right? Yeah.
Well, do we always have to simplify it so it's simple? Can you just leave it like where you got on the top instead of right there?
No, like, I expect you to simplify these.
Oh, all right.
I mean, you probably don't have to write it like this. I mean, if you let this as x to the minus 1, that would be fine. And in general, if the problem is such that you have to plug in an x value, then I really don't care to simplify. Right? As soon as you get there, just plug in the number and work with it. That's fine. But if the whole problem is to actually find the function, you're expected to simplify. Other questions? Yes?
Have fun.
Derivative x.
Huh?
Derivative x. Y equals derivative x plus derivative x.
So big
No.
All the same square root.
Oh, radical x plus, and then another one?
Have fun. Have fun.
Is that on the test?
I mean, you really think I put a problem like that on the quiz? So there are three radicals. So it's a chain rule within a chain rule within a chain rule.
Chain set.
So first we start with the outside function. It's a power function raised to the half, so we're doing the power rule. 1/2, leave everybody here. Minus a half, multiply now by the derivative of everything in here, right? So now the derivative of x is just 1. Derivative of this, you need the chain rule, right? So now you think of this as the outside function. You take a half times everything here, minus a half, and then you're going to multiply by the derivative of the inside, which is going to be 1 plus half x to the minus half.
Just leave it with that.
Yeah, I mean, I don't really see what we can simplify here. Yeah, I just sort of leave it like that. I don't really see this one. The book probably simplified it, but other questions?
41.
Cosine of square root of sine of tangent of pi x.
Square root of sine of tangent of pi x, like that?
Yes.
Yeah. Okay. Can someone tell me what they think I should do here?
So first, find the derivative of cosine.
Right. Well, first, remember that radicals are sort of annoying to think about. You can always rewrite this as the half power. So now, derivative of cosine is? So it's minus sine of all of this. Times, now we take the derivative of all of that, which is what? The half is the outside power, the outside function. You're going to do the power rule. Bring the half, leave everything intact inside, minus a half. Now you multiply the derivative of the inside. Derivative of sine is cosine, leave the inside function intact. Multiply by derivative of the inside. Derivative of tangent, secant squared, leave the inside intact. Multiply by derivative of the inside. So this is minus pi over 2 secant squared by x cosine tangent by x particle sine tangent by x. Other questions?
For the quiz.
No, we're doing the quiz at the end.
It is.
What happens to
Wait, you're going to do 2.6 first?
Yes.
what happens to the negative 1 half?
Wait, doesn't we have a
The exponent. What happens to the exponent? The negative 1 half?
Where?
1 half sine tangent by x to the negative 1 half.
Oh, this is supposed to be this. So this is like got a little negative sign. Huh? 42. The answer to life, the universe.
It's y
Spell that.
equals x plus, I don't know, x plus, parentheses x plus sine squared x.
X plus.
How do I explain that? Wait, it's this one.
Oh. These guys are trying to kill us with a chain.
Didn't you get the bone?
Like, when does that show up in real life? So you look at the outermost function, which in this case is the fourth power, so you're going to bring that down.
X plus sine squared x.
3. Now you multiply by the derivative of everything here.
So that's 1.
Open brackets, very important. Should have been emphasizing that before. Always open brackets once you're multiplying by the derivative inside.
1
So-
plus
Derivative of x is 1.
x plus
Now here, this guy, you use the chain rule again, right? Because there's a third power. Times we need the derivative of that.
Oh no, it's cube. It's not square.
Huh?
Is the square is not square. That's cube. You are finding the derivative of the x, the outside x. No,
I'm not sure. Where's the cube?
the x. You see the x. That's separate. X plus. Where are you
plus.
finding the derivative of that? First?
Yeah, derivative of the x is 1.
Yeah.
And then I want to find the derivative of this.
That would be the second step. You already wrote x squared. The outside. So then that becomes a cube. Is it?
Let me see what you're
So then that be cube. That one over there. You know
So the whole thing was to the fourth power, right?
Yeah.
So this gives me 4 this cubed, right? Which is this.
Yeah.
Now I want to multiply by the derivative of what's inside here.
Yeah.
Now it seems from what I wrote down, the cube is only applied to this part,
Yeah.
not the x. So I want to differentiate this. I differentiate 2 of these. It's the sum of functions. So I differentiate this one, then differentiate that
You
one.
can find derivative of 2 things at one time.
That's what I'm doing. Derivative of x is this, plus, now I'm finding derivative of this, which is a cube power I have to bring down, subtract 1 from the power, I get the square.
Okay.
And then I have to multiply by the derivative of the inside. So it's going to be 1 plus, how do I differentiate sine squared? Bring the 2 down, sine is the inside function, now you multiply by the derivative of that. Cosine. I didn't put anything that crazy.
Oh, wait.
That's crazy.
I don't think you'll ever see anything on the final that crazy. It's a good thing to like exercise your concentration to see if you really understand what the chain rule is about, if you can keep track of all your brackets.
We do 2.6 at the end.
Come again?
We do 2.6 at the end.
So that we don't.
It'll be much easier to take the quiz first.
Why?
Then I don't have to know all the 2.6 stuff.
You won't have to know for the
You're
quiz
gonna mix
either.
up all the information.
Oh,
I hardly got
bonus
information.
questions, right? We can get the bonus questions if we learn this.
What?
The bonus questions are on 2.6, right?
Well, that would be unfair. There's one question, bonus question on 2.6. And then the other one on 2.7.
Oh, so it will be unfair, so you can't. Come on, just give us the quiz
No, we should do 2 quizzes. What about we do the bonus question as a homework?
Why?
We do have the video rolling, so it would be a pain in the neck to break.
Quiz on Tuesday makes no sense.
You're going to change your mind.
Yes, but I'll give that at the end. Who wants 2.6?
Yeah, right.
Try to get through this quickly so we have as much time for the quiz as possible.
You can finish it all.
Nope, we're done.
Yeah. I mean, it's not that much really. It's really an application of the chain rule. That's all implicit differentiation is when you boil it down. First, some definitions. A function of x, say y, can be defined 2 ways. There's the way that we say defined explicitly. This means it's defined as y equals f of x, right? Where you can say y is explicitly a function of x. Did I give an example of that? Yes. Basically anything, pretty much almost everything you've seen before, like y equals x squared, or y equals the radical of x plus 1, or y equals x plus 1, or x plus 2. These are all explicitly defined. Y is out in the open, it's explicit, it's right there. Y equals some function of x. There's actually another way you can define things implicitly. This means it looks something like the y's and the x's are mixed together. You can't really separate them. For example, circles are defined implicitly. Right? Or xy equals 5 is defined implicitly. Or x squared y plus 2x. Right? So implicitly basically means you don't have something that's solved for y with only x's on the other side. The y's are mixed together with the x's. Right? Now sometimes you can solve for y easily like here, but other times you can't like here. Right? So in the explicit case, we can find y prime equals dy dx by previous rules. What about the implicit case, right? Now you might say, well, if you give me something like this, I can just solve for y and just find the derivative. But you can have guys like these where solving for y is probably not an option, not expedient, or sometimes just plain old impossible, right? So implicit differentiation is really meant to deal with this situation. If you're defining the function explicitly and you want to actually find the derivative of one of these guys, how do you do it? You use implicit differentiation. So that's the problem that it seeks to answer. The secret, the chain rule. Right, so say y equals f of x. Right? How would find the derivative of y. How would you find the derivative of y squared? How do you find the derivative of radical y? Well, what about x squared, y squared? X over y. Right? So this is just some background so you can see in the simple case how we're going to do it, right? So if we take ddx of y, what is the answer? Just dy dx, right? Can't really do anything, that's just the derivative, same plain old derivative that we have. But what if you had y squared? How do you do that? Yeah?
2y divided.
You get 2y dy dx. Can you explain why you would do that?
Because chain rule of first power will bring down the 2. And it's y.
Right. The idea is, right, it's exactly what you're saying. This guy, you have to remember that y is actually a function, right? You may or may not know what that function is, but you assume that you can write it as a function of x. Now, the chain rule deals with situations like these where you have a composite function. The chain rule would say, you're going to take the 2 down, leave the inside intact, 1 power here, then you multiply by the derivative of the inside. Right? Therefore, to differentiate y squared, you get 2y dy dx. Or 2y y prime, when you know that when the input variable is understood. Right? So radical y, how do you differentiate that?
1 over 2 y negative 1.
All right, you can rewrite this as y equals 1/2, and then use the chain rule, right? So this, you bring the half down, leave the inside function intact, subtract 1 from the power, then you multiply by the inside function, which is y, whatever it is.
2y to 1 over 2y 1 over 2.
So this is just 1 over 2 radical y dy dx, or 1 over 2 radical y prime, when the independent variable is understood. There are cases where this is preferable, but we'll get to that later, right? Because it turns out we can differentiate with things other than, with respect to things other than x. So I often write y prime because I'm too lazy to write dy dx. So you always, when you write it, you have to know what the input variable is. You can change them. What about this one?
First, you find the derivative of x. Use the chain rule, right?
You need the product rule, right? There's a product of functions. You have x squared times this other function. You have to use the product rule, right? All your old derivative rules apply. So this means you have to differentiate the first one, leave the second, right? Plus, now you leave the first one, differentiate the second one. We already differentiated y squared. This is 2y y prime. So the answer is 2xy squared plus 2x squared y and y prime. What's it on this so far? First of it. So the trick is to think of y as a function. It's some function, we don't know what it is, but we know it's some function, right? So we have to use the chain rule to differentiate them. What about this one? Right, looks like the quotient rule, or you can bring the y up and make it y to the -1 and do the product rule or the chain rule. It's up to you. As long as you apply an appropriate differentiation rule correctly. Let's say I want to use a quotient rule. So this is the bottom times the derivative of the top minus the top times the derivative of the bottom, which is what? dy dx all over the bottom squared. So I can actually write the derivative of this as y minus x dy dx all over y squared. It's up to you if you want to even write this as two separate terms, but you probably don't need to. There are cases where you're going to want to split them up. You'll see cases like that later. Are we okay so far? Any questions? Yes?
So at the end, we're going to end up with the y prime.
Right, our goal is to find y prime ultimately, right? So basically what we're going to be doing is we're going to have an equation where we're going to differentiate and we're going to try to isolate all these guys. That's going to be the idea. But I just need you to get down the basics down about how to differentiate expressions that have y's mixed in them, right? So notice that sometimes so like this case, right? Find y prime. Well, it's pretty easy to solve for y. We just say, you know, if x times y equals 1, this means that y is equal to 1 over x. This means that you just find y prime directly, right? So this is what? Minus x to the minus 2, right? Minus 1 over x squared, right? You could do that, right? This is done explicitly. Let's do implicitly with this example. How do you think you get this implicitly, right? Meaning find dy dx without first solving for y.
Take the derivative of each side.
Right, so the equation, what we're going to do is we're going to find the derivative of each side. Right? How do I find the derivative of this? Product rule. It's x times y. These are two functions, so I can use the product rule. Differentiate the x, leave the y, plus leave the x, differentiate the y, what do I get? Y dx. Derivative of 1?
0.
0. So now, what can I do? Remember, I want to find dy dx, so it just means I want to solve the equation for this guy, right? So this means that x dy dx is equal to minus y. So this means dy dx is equal to minus y over x. Right? You can leave it that way, but in this case, it's actually pretty easy to get that form. Just remember what y was. Y in the original was 1 over x, which would give you that minus 1 over x squared. However, in this case, implicit case, this is an acceptable answer.
It is negative 1 x squared, right?
Huh?
Negative 1 over x squared.
Yes, which is the same that I got here.
No, when you plug it in the y, it's just 1 over x.
Yes, y is 1 over x. Right? I could have solved for it from here
Oh, yeah.
and then just swap it out. However, like I said, there are many cases where you can't do that. You just leave the y there. It's okay to have the y's in your answer. So sometimes you can make things explicit easily. In that case, you just do it. Yes? You have a question?
Yes, okay. So implicit differentiation is what you want dy dx with the answer or to find it?
No, you want to find dy dx.
Okay.
It's just that your x's and y's are mixed up, right? You don't have y equals blah.
But over here, you wanted it in the answer.
What?
So the answer always came up to be having dy dx in the answer.
No, this was like doing one side of the equation, right? There was nothing to solve for it.
Just explicit, right?
I just wanted you to see what differentiating one side would look like. So here, this is what it would look like. Let's do another.
I
Yes.
just want to be clear, like the difference between explicit and implicit. So implicit is just like after you plug in the y.
No, explicit just means y equals this. That's it. You have y on one side and nothing but x's on the other side. Right? That's explicit. Implicit means things are mixed up. You can have, function of x and y, right? You have x's and y's mixed together on one side of the equation. Right? That's called implicit. Right? That's it. It's just how it's presented. So this equation and that equation, they're the same equation. This is the implicit form, this is the explicit form. Right? It's just a matter of how you express it. So sometimes you can make it explicit even if you're given it implicitly. And if you can do that if it's there, right? Sometimes though it's not expedient. Even if we can. So an example would be something like find y prime if, here's the question, 5x squared plus 2x y plus x to the fourth y squared equals 4x cubed. It turns out here we can solve for y. Want to. How do you solve for y here? My masters of algebra. You can factor that?
Yeah, but you still have to wind up.
Huh?
Subtract y.
Subtract what?
4x during your power.
Okay, and then what?
And then distribute y and then the whole function.
And then distribute the y?
Yeah, and then find all the derivatives. And then do
I'm saying solve for y. No, don't worry about derivatives.
Oh.
Like, could you rewrite this as y equals something?
You
I mean, I think you could, but it would be.
Yes, distribute.
Oh no, actually you couldn't because.
Divide by one.
No, you can't because y and the other y wouldn't add up. Because y to the second will be. And that's x to the fourth, y to the second, the other one will be x to the second and y to the second. You'll have y on each side. I don't think you could do it.
You don't need to be though. You're making us think about it.
You guys are the algebra masters. I'm asking for help.
can't really solve it.
Could you solve that for y?
No. Subtract it.
How?
Oh.
Like 2x squared plus
What?
Y equals.
Forget quadratic formula, right? Minus b plus or minus the square root of b squared minus 4ac all over 2a, right? It's just that here your constants have x's, right? You can think of this as the a, that is the b, that is the c. You can actually use the quadratic formula to solve for y, if you were so motivated. The problem is though, your b is going to be this huge function. What's under the square root is going to be this squared minus 4 times this times that. All over 2 times this. You get a function where you have to use the quotient rule and a crazy chain rule in the middle of it, right? So yeah, in theory, I could solve for y. I could do it. Do I want to do it?
No.
If I want to find the derivative? No, right? So there are cases like these where implicit differentiation comes to your rescue. You don't have to do all that hard work.
Are you going to solve it?
So yeah, that's something I could solve for y, but I wouldn't want to, especially what I'm after is the derivative. So let's actually do it. So we have 5x squared plus 2x y plus x to the 4th y squared equals 4x cubed. How do I find y prime?
We have half an hour left, right?
Sounds straightforward. Just have a whole time.
Alright, we're going to differentiate both sides, right? Derivative of this part.
Yeah, you distribute for it first.
No, I wouldn't distribute that. I do product rule, right? Derivative of this times that. Plus the derivative of this times that. Plus, what about here?
4x cubed y squared plus y squared.
No. 2y prime, right?
Yeah.
Differentiate that. Equals derivative of this.
12x squared.
So how do I solve for y prime?
Now you separate the y prime.
I want to isolate them. I have a y prime here and a y prime here, which means everyone who doesn't have it, put them on the other side, right?
Yeah.
So here I have 12x squared. I subtract this. Subtract this. That's it. And then, right now, y prime is a common term. I can just factor them out and then divide by the coefficient.
Well, Professor, write down the 2x to the 4th.
What? The 2x to the 4th came from here.
Oh.
And that would be your answer. It's okay to have y as an answer because you don't want to solve for it.
Professor?
Yes.
You forgot a y in the denominator.
2 raised to the 4th one. Okay, so sometimes it's easy to make it explicit. In that case, you can do it. Sometimes you can make it explicit, but you don't want to. Sometimes it's impossible to make it explicit. Example. Find y prime if squared plus y to the 7 minus 2y equals 3. Now, for those of you in the know, you know that there is no quadratic formula for a 7-degree polynomial, right? The highest power here is 7. So unless this thing factors really nicely by like grouping or difference of two squares, there is no hope. This function, for example, we know does not factor very well because you can't even write y as a function. If you look at the graph of this guy, it actually looks like that. It fails the vertical line test, right? So you can't express y as a function of x, right? So, but we can still find the derivative at any point. I can still find the slope of the tangent line to any point of this that I want. Implicit differentiation. 2x plus 7y to the 6 minus y prime minus 2y prime equals 0. There, you have two classes. So this is 7y to the 6y prime minus 2y prime equals minus 2x, which means your y prime is equal to minus 2x divided by 7y to the 6 minus 2.
Okay. The derivative of x squared is 2x. Then
Yes.
the derivative of y to the 7 is 7y to the 6.
7y to the 6 times y prime, because the chain rule, right? Remember the y is like this function that's in there.
So why wasn't there a y prime with 2x? So there's no y?
You think derivative?
There's no y. X squared is just a power rule, right? You differentiate x squared by the power rule.
Okay. Where did 3 go?
Derivative of 3 is 0.
Oh.
Derivative of constant. Let's do a couple more examples. You guys try these on your own and then we'll go into the quiz. Find y prime for those. Forgot I actually wanted to find the tangent on here. I guess we can do that.
Should I stop this?
No, we're going to do this. I'm waiting for some brave soul to tell me the answer. Huh?
Sine y.
You think you got this one?
Yeah. Sine y plus 6x over 2 minus cosine y.
Sine y plus 6x over 2 minus cosine y, that's your answer.
Yeah.
How'd you get it?
Yeah, plus chain rule and then differentiation.
Okay, so this would be differentiate x, leave the sign, plus you leave the x, you differentiate the sign,
I forgot to add
times y prime, because the y is like a function inside this cosine. Then plus this 6x equals 2y prime.
It's divided by 2. You got negative brackets.
Where? Now what?
Let's subtract the 2y prime.
To move this over here, x cosine y prime minus 2y prime is equal to, bring these two over, minus 6x minus sin y.
Yes.
And so y prime would be minus 6x minus sin y over x cosine y minus 2. So almost missed the x here. This is the same as 6x plus sine y over x over 2 minus x cosine y. If you don't like the negatives in the top. Anyone tried this one? Yes.
Why did you bring sine on the other side? Because it's y, so you just stay with the y side.
The goal is to solve for y prime. Right? Remember, find the derivative is the goal. Anyone who doesn't have them, bring them to the other side. It doesn't matter if there's a y in your answer.
Wait, Professor.
So why doesn't it have a y prime?
What do you mean?
Oh,
The y prime here is a constant. I factored it out. And then I have x cosine y minus 2. And then I divide both sides by that.
Professor, you see over there? You move on to the last step. Yeah.
Yep.
Go up a little bit. Can you get it there?
Yeah, that's fine. Anyone want to try this one?
Yeah.
Yeah? Alright, go. How do you differentiate that?
You put it x, y, brackets, 1 over 2.
Oh, you want to rewrite it first? That's fine.
Yeah.
Okay. 1 over 2 plus cosine y plus 10 plus x squared. Alright.
Then it gets 1 over 2, x, y, negative 1 over 2, plus negative sine y.
Nope.
Oh, you find the derivative of inside.
Just find derivative inside of here, right?
Yeah, yeah.
Multiply. Now
So
what's
that
that?
would be just y plus x dy over dx.
Like prime, dy dx is right.
Then negative sine y,
Here?
negative sine y, plus 2x
Nope.
equals plus 2x.
Nope.
prime.
You need a y prime here, because there's an inside function, right? Don't forget that y. Whenever you differentiate something with y's in it, you have to attach y prime. Equals. So now the goal is solve for this guy. How do I solve for that guy?
That's y, and then 1/2 to the right.
Nope. What do you factor?
You take the dy dx outside.
How?
By taking out the y prime. Just take out the y prime.
So I can just take out the y prime?
No, you probably have to
Just take out the y prime. Multiply.
Distribute.
Yeah, multiply everything by y prime.
what rule did you use?
Distributive law.
No, before
Where?
that.
Here?
Yeah.
Chain rule. The outside function was a half power. Bring this down, take this to the minus a half, I get this. Then I have to multiply by the derivative of the inside. That is a product of functions, so the product rule applies. So I have to do differentiate the x, leave the y, plus I leave the x to differentiate the y. And that's done. Then I move on to the cosine. That is minus sine y. Y is the inside function multiplied by its derivative. You get y times. Derivative 2 is 0. Derivative x squared is 2x. Now I want to solve for y prime. So what I'm going to do is I'm going to break it out of the brackets. So now I can keep these two on one side, bring everyone else to the other side. So now this means y prime is equal to 2x minus 1 half xy minus a half y. Oh yeah, this is a pretty normal problem. Yeah.
I think the third step down. The first intersection. The first part.
Where?
No, that's it.
The starting point.
Yeah, so here I just left, right? This I just recopied. I took this guy, moved it to the other side. So that's 2x minus this guy. And then I factor out the y prime, divided by that. Okay, we'll finish up 2.6 next time. For now, get ready for the quiz.
So we are not done with 2.6.
We're not done with 2.6, that's right. That's enough.
That's something.
Yeah.
Professor, did we stop the video now?
Yes, we can stop.